now that I am finished with the fundamentals of X-ray crystallography, I shall concentrate on various important applications of X-ray diffraction. The reason why we must have diffraction from a material when an X-ray beam is incident on it is a fact that we must have some information out of that material or that crystal in the form of a diffracted beam that will contain all the information that there is to see within the crystal or within the material. Now, one of the most important applications of X-ray diffraction is the determination of crystal structure. For this purpose, what we do is we index a diffraction pattern. So, what is meant by indexing? By indexing, we mean we look at all the diffraction lines in the pattern, determine the HKL values of all the planes that give rise to the diffraction lines, determine the crystal structure and the Bragg lattice from these diffraction lines, and finally also determine the lattice parameter or parameters very precisely. Now, normally when we do a diffraction analysis from an unknown sample, just by looking at the diffraction lines and their positions and their intensities, it is in most cases not possible to figure out which crystal system the material belongs to. So, in a way we can say that determination of crystal structure of an unknown material is more or less a trial and error method. For example, when we do a X-ray diffraction from a particular material, we get the diffraction data in the form of diffraction lines. We initially assume a particular structure for the material in an intelligent way. Then from there we try to calculate what should be the diffraction pattern like. Then we find out if the results match the experimental values. If yes, we can be assured that our assumption is correct. Then we start indexing the diffraction lines accurately. From there we determine the crystal structure, find out the Bragg lattice, and then calculate the lattice parameter or parameters. If on the other hand we find that the calculated diffraction pattern does not match the experimental values, then we repeat the process with a different assumption. Now, here I shall discuss how to determine the crystal structure, Bragg lattice and lattice parameter from the X-ray diffraction lines of an FCC material, a BCC material and an HCP material. Say for example, this is an XRD pattern of an unknown substance. Now, to begin with, we assume the simplest possible crystal system for this material, which is cubic. So, we assume the material has a cubic crystal structure. Now, the first thing to do is to determine the distance between each of the line pairs which appear on the diffraction pattern. Say this is the line pair 1 1 coming from a particular diffraction from a particular HKL plane, then these two are the 2 2 line pair which appear due to diffraction from another particular HKL plane. This is the 3 3 line pair which is due to diffraction from a third HKL plane, etc., etc. So, the first thing to do is to measure the distance between the any line pair. So, this we do using a rectangular box of this type, which has got a glass plate here, below which there is a source of light, so that all the lines on the pattern are shown very clearly. There is a graduated scale along with a vernier in order to measure the line positions very, very accurately. Say for example, this is my line pair 1 1. So, this is the position 1 for this line pair, this is the position 2 of the line pair. So, we find out with the help of the scale and the vernier what are the values here and what are the values there, and then we subtract one from the other. So, in this way we find out that this value 2s for this line pair is simply equal to 2.81 centimeter say. Now, if we will recapitulate what we did in case of the description of the Debye-Scherrer method, if we choose a low angle diffraction line, say the plane has given rise to the diffracted beams over here. So, this distance on the film is the distance 2s, as we have already seen. Now, we can easily write this length, which is 2s, divided by the circumference, which is pi times d. D is the diameter of the camera. Here there is a mistake, it is the camera diameter, not camera radius. So, 2s divided by pi d will be equal to the angle subtended here is 4 theta, and the angle subtended by the whole circumference is 360. So, from this relationship, since d is known, the camera diameter is known, s has already been measured, we can find out the value of theta for this particular line. In this way, for all the low angle diffraction lines, we can measure, we can find out the corresponding theta values, corresponding values of the Bragg angles. Now, if we are looking at a high angle diffraction line on this side, then say this is where the high angle diffraction lines are found for a particular atomic plane. So, since this is the X-ray in direction and this is the direction of diffraction, this will be 2 theta. As a result, this angle will be pi minus 2 theta, this angle will also be pi minus 2 theta. So, if we measure the distance between this line pair, if it is 2s, and if we divide it by pi d, so it will be equal to 2 times pi minus 2 theta, which is 2 pi minus 4 theta divided by 360. from this relationship, since S has been measured and since D is known, we can easily find out the value of theta, the Bragg angle. So, in this way, for all the lines in the pattern, whether in the low angle side or in the high angle side, we can find out the value of theta, the Bragg angle. Say for the particular case, we have 8 lines and say we have measured all the 2 S's in this fashion, from which I can find out the value of theta for each line pair, I can find out the value of sin theta for each line pair, I can find out the value of sin square theta for each of the line pairs. So, to begin with, we assume that the material has the simplest crystal structure, say cubic. Now, if we have a cubic material, the relationship between the interplanar distance of a set of planes and the HKL values of that plane can be stated as 1 upon d square is equal to h square plus k square plus L square divided by s square, where A is the lattice parameter of the material. Now, we know that Bragg's law states that lambda is equal to 2d sin theta. So, if we combine 1 and 2, by combining these two we can write sin square theta is equal to lambda square by 4 s square multiplied by h square plus k square plus L square, where lambda is the wavelength of the incident radiation. It is a Debye-Scherrer method, it is a powder method. So, lambda is a constant value. Now, A is the lattice parameter of the material, so that is also a constant value. So, in this equation here, lambda square by 4 s square is a constant for all the lines in the pattern. Therefore, we can write sin square theta is equal to k times h square plus k square plus L square, where k is a constant for all the diffraction lines in the pattern. If that be the case, we can write down for line number 1 or line pair 1, sin square theta 1 divided by h 1 square plus k 1 square plus L 1 square should be equal to sin square theta 2 for this line pair number 2 divided by h 2 square plus k 2 square plus L 2 square equal to sin square theta 3 divided by h 3 square plus k 3 square plus L 3 square is equal to k. Now, here there is a mistake, please read sin square theta 3 here, and these are h 3, k 3 and L 3. So, 1, 2 and 3 etc. refer to the lines in the pattern. So, we come to a very important conclusion that if we divide the sin square theta values of the different lines by their corresponding h square, k square plus L square values, then for every line that will yield the quotient k, a constant. Now, you see that h, k, L are all integers. So, h 1 square plus k 1 square plus L 1 square, or h 2 square plus k 2 square plus L 2 square, or h 3 square plus k 3 square plus L 3 square, these are all individually integers. So, the relationship states simply this, that if we divide the sin square theta value of line number 1 by an integer, it will be equal to sin square theta value of the second line divided by another integer, and that will be equal to sin square theta value for a third line pair divided by still another integer etc. equal to a constant value. Now, what are the values which h square plus k square plus L square can assume? This is very important to know. So, we know that h square plus k square plus L square can assume only a certain values, not every value. Now, if suppose we find that this kind of a relationship is true for each and every line in the pattern, then we can say that this pattern must be from a cubic material. Unless and until the material is cubic, this kind of relationship will not be satisfied. Say for example, if H, K and L are such that H is 1, K is 0, L is 0, then what will happen? If H is 1, K is 0, L is 0, then H square plus K square plus L square will be simply 1. If H is 1, K is 1, L is 0, then it will be 1 plus 1, 2. If H is 1, K is 1, L is 1, then it will be 3, etc., etc. Now, in this particular case, just if we divide the sin square theta value for line pair 1, 1 by 3, then we shall see that this will be equal to the sin square theta value of the line pair 2, 2 divided by 4, and this will be equal to the sin square theta value of line pair 3, 3 divided by 8, and so on. Say for example, we prepare the following table. So, these are all the 8 lines we find on the pattern. These are all the 2s values for all the line pairs. This is the value, these are the values of theta, sin theta and sin square theta calculated from 2s values. And here we have got a chart, sin square theta divided by 1 for all the 8 line pairs, sin square theta divided by 2 for all the line pairs, sin square theta divided by 3 for all the line pairs, sin square theta divided by 4 for all the line pairs, by 5, by 6, etc., etc. From this table we find that line 1, 1 for the line 1, 1, line pair 1, 1, if its sin square theta is divided by 3, it gives you a value of 0.047. Again we find that sin square theta of line pair 2, 2, when it is divided by 4, it gives us a value of 0.047. And when we divide the sin square theta value of line number 3 by 8, it gives us a similar kind of value, 0.046. And if we go to the 4th line and divide its sin square theta by 11, it becomes 0.046. So, that indicates that for line pair 1, 1, if we divide sin square theta by 3, that becomes equal to the sin square theta of line pair 2, 2 divided by 4 becomes equal to sin square theta value for line pair 3 divided by 8, that becomes equal to sin square theta of line number 4 divided by 11. So, it appears the pattern has been taken from a cubic material. Now, in this way, if we carry on, in fact, we can find out that this is true for all the 8 lines in the pattern. For example, the sin square theta of the 6th line, when divided by 16, it also gives the same value as we had before. Then for this particular line, 7th line, sin square theta is divided by 19, also gives us a similar value, 0.045. Sin square theta by 20 for the 8th line gives us a value of 0.045, the same value. So, you see that for each and every line in the pattern, if we divide the sine square theta of a particular line pair by an integer, we find that the the result is the same for every one of the lines in the pattern. So, if we know the value of the h square plus k square plus l square for any line pair, we can easily write down what are the h, k, l values for those lines. Say for example, here for line number 1, this 3 is the value of the corresponding h square plus k square plus l square. This is where for line number 2, 4 is the value of h square plus k square plus l square. So, if here h square plus k square plus l square is 3, and if for line 2 h square plus k square plus l square is 4, that indicates that in this particular case h, k, l will be 1, 1 and 1, and what about this? The h, k, l will be 2, 0, 0. Similarly, if we find for the third line, 8 will be the corresponding h square plus k square plus l square for the line number 3. So, since it is 8, we can write h, k, l as 2, 2, 2, etc., etc. So, in this way we can immediately write down the h, k, l values of the different lines. Say for line number 1, it will be 1, 1, 1, line number 2 is 2, 0, 0, line number 3 2, 2, 0, line number 4 1, 1, 3, line number 5 2, 2, 2, 6, 4, 0, 0, line number 7 3, 3, 1, line number 10 8, 4, 2, 0, etc., etc. So, you see that initially we assumed that the material is the simplest possible type. It has got the cubic crystal system, and we found out that the condition for a cubic crystal system has been fully satisfied by dividing the sine square theta values of the different line pairs by some integers, which are nothing but h square plus k square plus l square values for the different lines. And since this relationship is fulfilled for each and every line of the pattern, we can immediately say that the material is indeed a cubic material. So, crystal system is cubic. Now, looking at the h, k, l values, what we find, the h, k, l values are such that they are all unmixed, that means either all odd or all even. Say for example, here it is all odd, all even, all odd, etc., etc. We know that when we have a face centered cubic material, this is what happens. The h, k, l planes which are unmixed, that means either all odd or all even, they will give rise to diffraction patterns. So, immediately we can come to the conclusion that the material has a cubic crystal structure. Not only that, the Bragg lattice is FCC type. Now comes the third part of the problem, how to determine the lattice parameter of the unit cell in the material under investigation. Now, this can be done from this relationship which we found out earlier, that for any line sine square theta is equal to lambda square by 4 s square into h square plus k square plus l square. So, we have now for every line found out the value of h square plus k square plus l square and the corresponding sine square theta value. Now, lambda is known, this is the wavelength of the incident radiation, which is copper K alpha radiation in this case, that means 1.542 angstrom. So, from this relationship the value of A can be easily determined, and once we do that we can write down the value of A for calculated from each and every line. So, this is the value of A for calculated from line number 1, this is the value of A calculated from line number 2, this is the value of A calculated from line number 3, etc., etc. Now, the question might be asked that A is a lattice parameter and it is a fixed quantity. So, how come we are getting all different values? Now, you have to remember that whenever we do the calculations, we make some manual measurements. For example, 2s values we determine manually. Now, these values when we measure, there will always be some personal error, and it is because of this that when we calculate the lattice parameter from the different lines, the values appear to be different. But for some reason which I will explain later, we take the lattice parameter determined from the highest angle line in the pattern to be the most accurate. That means, out of all these A values we have calculated from the different lines, we will consider this one calculated from the highest angle line in the pattern to be the most accurate. We will find out the reason why very soon. So, we have found out for an unknown sample what is the crystal structure, what is the Bragg lattice, and what is the lattice parameter. Now, let us take a second example here. Say this is a powder pattern obtained from material using a Divisorer camera, and these are the different line positions on the film. Now, as we have done in the previous method, we calculate, we determine, or rather we measure the value of 2s for each line pair and write them down. Now, from these 2s values, we can find out the corresponding theta values, the sin theta values, and sin square theta values. So, this is an unknown sample. So, how to start with? First of all, we assume that the material has the simplest crystal structure. So, we assume a cubic system for this unknown material, and we know that it is quite easy to determine whether the material belongs to the cubic system or not. Say for example, we find in this case, if the sin square theta value of line number 1 is divided by 2 is the same as the sin square theta value divided by 4 for the second line is the same as the sin square theta value divided by 6 for the third line is equal to sin square theta value divided by 8 for the fourth line is equal to sin square theta value divided by 10 for the sixth line, for the fifth line, so to say. So, you see that all these values are almost equal. Then that gives an indication that, well, like the previous case, this material may also be belonging to the cubic system, and in a manner which has already been described for the previous pattern, we can immediately write down the corresponding HKL values from the h square plus k square plus L square values for each and every line. And what we find here, the HKL values are such that H plus K plus L is an even quantity. So, the HKL values of the lines are such that H plus K plus L equal to 0 equal to an even number in each case, and this is the condition for a body centered cubic structure. If a material has a body centered cubic structure, we know that H plus K plus L must be equal to an even number, and this is what is true in this particular case. So, now we have determined the crystal structure and Bragg lattice for this unknown material. Now, we find out the value of A from the known relationship that exists between A and HKL as we did before, and the values of A calculated in this manner are found to be this. So, you see that there is a wide variation in the value of A which has been calculated. Now, as I told you before, we take the A value from the highest angle line as the most correct value of A. So, we consider this to be the most correct value of A. Let us now go to a third case. Say we have got a diffraction pattern for an unknown material here. Now, the first step is to measure the 2s values for each line pair as we did before. Say when we do it, there are about 13 lines in the pattern, and these are all the 2s values. Now, if we deal with these values and assume that the material is a cubic material, we know how to figure out whether the material is a cubic material or not. So, we apply the same criteria which we did before for the first two samples, and if we do that, we find that the lines in the pattern do not satisfy the requirement for a cubic material. So, we have to think again. So, it may be tetragonal, it may be hexagonal, it may be orthorhombic, whatever. So, let us assume that this material has a hexagonal crystal structure. Now, if we think about a hexagonal crystal structure, then the relationship between sin square theta HKL and HKL are given by sin square theta is equal to A into H square plus HK plus K square plus CL square. Now, we remember that in this particular case, we have got 3 axes of the same length AAA in one plane and C axis perpendicular to the plane containing the 3 A axes. Now, in this equation, capital A stands for the lambda square divided by 3s square, and capital C stands for lambda square by 4c square. So, a and small c being the lattice parameters and lambda being the wavelength of the X radiation that we use. Now, as we did in the previous two cases, from the 2s values for each line pair, we calculate the value of theta, sin theta and sin square theta in the usual manner. Now, when we look at h square plus hk plus k square, putting different values for h and k, we find that h square plus hk plus k square can have the values 1, 3, 4, 7, 9 and so on. In this case, h is equal to 1, k is equal to 0. So, h square plus hk plus k square is equal to 1. Then if h is equal to 1, k is equal to 1, then h square plus hk plus k square is equal to 3, etc., etc. So, these are the possible or permissible values of h square plus hk plus k square, that will be 1, 3, 4, 7, 9 and so on. To make life easier, let us consider only the first 6 lines in the pattern: line pair 1, 1, line pair 2, 2, line pair 3, 3, 4, 4, 5, 5 and 6, 6. These are the 2s values, these are the theta values, these are the sin theta values, these are the sin square theta values. Now, what we do? We divide the sin square theta values by 1, 3, 4, 7, etc., which are the permissible values for h square plus hk plus k square. Say for example, if there are some lines having the indices h, k, 0, that means L is equal to 0. So, there may be some lines, may or may not be, there may be some lines for which the L is 0. So, these are HK 0 type line pairs. So, if we have got such lines in the pattern, then the equation sin square theta is equal to A into H square plus HK plus K square plus CL square can be written simply as sin square theta is equal to A into H square plus HK plus K square for HK 0 type of lines. If it is HK 0 type of lines, L will be 0. So, in that case, this equation can be written in this form. Therefore, we can write from this equation sin square theta divided by H square plus HK plus K square must be equal to A, which is a constant for all the lines. Now, if we go back to the previous diagram here, we will see that sin square theta by 1 for line pair 2 2 is equal to sin square theta value by 3 for line pair 5 5 and is equal to 0.108, as it is becoming quite clear. So, you see that for the line pair 2 2, the sin square theta by the sin square theta by 1 for line pair 2 2 becomes sin square 2 by 3 value for the line pair 5 5 and the value is 0.108. So, these are the values which we obtain. So, what does that indicate? It indicates that it could be that the line pair 2 2 and the line pair 5 5 could be HK 0 type lines. So, it appears this could be the HK 0 type lines. Therefore, if L is equal to 0 for these two line pairs, then H square plus HK plus K square for these two lines can be taken as 1 and 3 respectively. So, once we do that, we can immediately find out if the H square plus HK plus K square is 1, that means the line will be 1 0 0, and for line pair 5, H square plus HK plus K square is equal to 3, that means it will be the line 1 1 0. Okay? Now, if we go back to the previous diagram, so we can see that the HKL for the line pair 2 2 can be tentatively written as 1 0 0, and the HKL value for the line pair 5 5 can be tentatively written as 1 1 0. Now, if we consider the line pair 2 2 only and substitute the value of sin square theta, which is 0.108, and H square plus HK plus K square is equal to 1, then from this equation we can find out the value of A constant, which is 0.108. Now, what about the indices HKL of the other 4 lines in the pattern which do not have 0 L value? Then we follow the following procedure. Say from the equation sin square theta is equal to A into H square plus HK plus K square plus CL square, we can write it in this form: sin square theta minus this term is equal to CL square. Now, we already know that H square plus HK plus K square can assume values of 1, 3, 4, 7, 9, etc. So, if we subtract the values of a into 1, a into 3, a into 4, a into 7, a into 9, etc., then these values for the other 4 lines should be related to one another in the ratio of 1, 4, 9, 16, etc., corresponding to the values of L is equal to 1, 2, 3, 4. So, what I am repeating the whole case, you see, from the basic equation we can rewrite the terms in this fashion. Now, we know that h square plus hk plus k square, they can have values of 1, 3, 4, 7, 9, etc. So, the other 4 lines, if for the other 4 lines, if we subtract a into 1, a into 3, a into 4, a into 7, a into 9 from the corresponding sin square theta values, then the values so obtained should be in the ratio of 1, 4, 9, 16, etc., because L can assume values of 1, 2, 3, 4, etc. Now, using this logic, the value of the line pair 3, 3 is 0.024. The values of the line pairs 1, 1 and 4, 4 are 4 times that. The value for the line pair 5, 5 is 9 times that. The value for the line pair 6, 6 is 16 times that. Now, if we go to the next diagram, it will be quite apparent. So, you see that we have already found out that if we take the line pair 3, 3 as shown here, if you do at the line pair 3, 3, now this has got a value of sin square theta minus a into 1, okay? Because here we have plotted, we have determined 2s theta sin square theta, then sin square theta minus a into 1, sin square theta minus 3 a into 3, etc., etc. So, here we find that this value here for line pair 3, 3 is 0.024, whereas this value here, which is sin square theta minus 0 into a, is 0.096, 4 times. This is also for line pair 4, this is also almost 4 times this value. This is 9 times this value here, and this is 16 times the value over here. So, tentatively, if we can put L is equal to 1 in this case, then this L will be 2 over here and 2 over here, then it will be 3 over here and 4 over here. That means, if L is 1, 2, 3, 4, then the corresponding values will be like this, that one is if this is L is equal to 1, then this will be L is equal to 4, this is L is equal to 2. So, it will be 4 times that, and it will be 9 times that. So, correspond if this is L is equal to 1, this will be L is equal to 3, this is 16 times this value. So, if this is L is equal to 1, this will be L is equal to 4. Now, if we do that, we can immediately write down the L value for the line pair 1, 1 as 2, L value for line pair 3, 3 as 1, L value for line pair 4, 4 as 2, L value for line pair 5, 5 as 3, and L value for line pair 6, 6 as 4. And what about the hk values? Since here h and k, h square plus hk plus k square, how much it will be? this is sin theta, this is sin square theta. So, sin square theta minus 0 into that means h and k must be 0. So, we can write down 0 0 here as the indices h and k. Here for example, we find how much will be the h square plus hk plus k square over here. In this column, h square plus hk plus k square must be equal to 1. So, for this h and k must be 1 and 0. So, we write down 1 and 0. What about this line? This also comes under this column where h square plus hk plus k square is simply equal to 1. That means h and k are 1 and 0. So, we write down h and k values as 1 and 0. What about this value? Here it also comes under this column. So, h and k must be 1 and 0. So, we write 1 and 0. And what about this value? It comes under this column where h and k are 0 and 0. So, we can write 0 0. And this we already determined earlier, and this we have already determined earlier. So, you see that line number 5 can arise due to both the planes 110 and 103, and they will appear at the same place because D is the same for both kinds of planes. So, now we have found out the HKL values of all the planes which will give rise to diffraction in this particular case. So, we have been able to index all the lines by using the same logic. Now, we already know that for the line pair 1 1, h square plus hk plus k square is 0. Therefore, when we substitute for sin square theta, it will be 0.096, h square plus hk plus k square is equal to 0, and L is equal to 2. In the equation sin square theta, and when we put these values in the equation sin square theta minus a into h square plus hk plus k square equals CL square, we get C is equal to capital C is equal to 0.024. So, we have already calculated the value of the capital A and the capital C, which are constants for all the lines in the pattern. Since capital A is lambda square by 3 a square and capital C is equal to lambda square by 4 c square, and the lambda, the wavelength of the radiation we used was 1.542 angstrom. Substituting all those values in the above two equations, we find A, the one of the lattice parameters, as 2.710 angstrom, and the C is equal to 4.974 angstrom. Now, the C by A ratio is 1.835, which shows that it is a hexagonal close packed structure. You see, this is wrong to say that this is a Bravais lattice. This is not a Bravais lattice. So, this material that we have examined is a material which has a hexagonal close packed structure. Now, we talk about the modern method. You see, nowadays we use the X-ray diffractometer in most of the labs instead of the cameras for the determination of crystal structure of known and unknown materials. Now, diffractometer output comes out in the form of a paper chart showing the locations and intensities of diffraction lines as shown on the screen. So, this is the intensity of a diffraction line, and this is the 2 theta along x axis. The 2 theta values for the different diffraction lines can be easily determined from the chart, so that you can figure out the exact 2 theta values for the different lines over here. All these high intensities lines are similar to the lines which appear as lines on a photographic film in the Divisorer camera. So, one advantage of the diffractometer method is you can accurately read out the value of theta for each and every line from the chart. And once you determine the value of theta using the same method as before, we can find out the value of sin theta and sin square theta, and from there we can follow the same procedure as we did with respect to Debye photographs. So, in this way, if you have got a diffractometer plot, from that also we can easily figure out the values of theta for each and every line straight away, and then from there we can measure sin theta, we can determine the sin square theta, and then deal with these numbers in the same way we did for the Debye photographic method, and determine the crystal structure. Now, in the next chapter we shall be dealing with how to measure the lattice parameter or the lattice parameters very, very precisely. For example, we have already seen that depending on the calculation, depending on the diffraction line from which the A values are determined, there are different values of A or different values of C, but actually these are constants for the material, and as I have already said that this arises due to error in the measurement of 2s or error in the measurement of theta. So, in the next chapter I will deal with the technique or method of determining the lattice parameter or parameters very, very precisely.